Professor. Thank you for a very interesting talk, and also thank you for letting us do this interview with you.
It's my pleasure. It's really my pleasure.
So, like, you are quite well known in the field of nanophotonics for your contributions, but I would like to start this interview and ask you, like, how did you get into science, and what shaped your path towards your current research?
So my father is a physical chemist, and he was a professor. My sister is a grade school science teacher, and two of my children studied chemistry. My third son studied engineering, and I studied chemistry. So the joke in the family is that we just have some kind of genetic tendency towards science. But of course, it's hard to know if when you have a parent who's also a scientist, how much they're influencing your interests. But I was always interested in science and technology, and also with an eye on doing research in academia.
That's quite interesting. So coming to your research, like today you mentioned about Fourier pixels. When we say pixels, in general, the idea that comes to our mind is like the pixels from cameras or like display screens. So are Fourier pixels similar to that, or it's like a completely different way of, understanding light?
So it would be exactly like the normal pixels that we're all used to, but just have additional capabilities. So if I joked about it in the lecture that you were at, that at the beginning of this project, I challenged researchers in our group that I wanted to make this Princess Leia 3D hologram that R2-D2 projects. And so to make such a 3D hologram, you have to have much more control than you have in a current television, right? So a television is not projecting a hologram that we can see as 3 dimensions. And so these Fourier pixels that we're developing could in principle make such images, so 3-dimensional looking images, but many other things. It's like hard to imagine now, since we just did it, where exactly the field is going. I think that's an important point for young people to realize, is that sometimes you're moving in some direction and you don't really know where it's going yet.
So like in the future, do you think like this kind of optical control technologies could be implemented in your imaging systems or like devices?
Yes, no, absolutely. So I mean, that's what we're thinking now, is trying to, we've made individual pixels, but the idea would be to maybe make an array, just like in a television has a array of pixels. And maybe the pixels that we put on this grid or this array each does something different, and we're controlling them to make some projected image or sense something coming in. But these are the next research questions that we're going to try to address.
I also remember, like you said, like you use kind of like structures that are like sinusoidal or wave-like patterns to develop this kind of Fourier pixels. So would you like to share us like what influenced you to use this kind of structures to develop Fourier pixels? Like what's the idea behind this, like for general public?
Sure. So, and this wasn't my idea. So fortunately, as a researcher, you often get to work with very smart people, and a doctoral student in our group learned how to make wavy surfaces, and we were trying to figure out, well, what would this be good for? Nolan Lassaline is his name. And then he thought about the idea that anytime light hits a surface, light is a wave. And as a wave, it's looking for the waves in the surface profile. So if it's a flat interface, it doesn't have any waviness to the interface, and the light wave would just bounce off. But if it has some waviness to the interface, then you can get all of these more complicated effects like that would produce holograms. So he actually came up with this idea. And the fact that it's so simple, as I was stressing in the talk, this really resonates with me. We're always looking for ways to do complicated things, but in the simplest possible way. You
are very well known as an excellent teacher. So I would like to ask you, like, if your teaching experiences have made you think about your research problems in a different way that otherwise wouldn't have possible?
It's hard to pinpoint a specific example. I think it's probably much more indirect. And certainly early in my career, when I was working on nanoparticles, they are called colloids. And at the time, I started teaching a course on colloidal chemistry. And that gave me a lot of background information that I can't pinpoint an example of where it affected my research, but certainly having this knowledge from teaching something is important. And then when I moved to ETH, I started working on plasmonics, and so I decided to teach a course on plasmonics, and that was super good again for me to really learn the subject well. So that certainly applies, but I can't pinpoint an example like where I was teaching a lecture, something on the chalkboard, and suddenly I had an idea about something we were going to do in research.
Like we also learned that like your career spanned across industry and also the academic systems both in the US and now in Europe, right? So like what are the like differences that you find in research like based in academy and industry and also in like US versus Europe?
Yeah, that's a very complicated question because we're talking about differences on multiple axes. So maybe first industry. So I started out in industry, it's correct. And when students hear that I was working in an industrial lab, they think I was, really working on problems that the company I worked for needed solved, like for the next product that was coming out in 6 months. But I was working in their most long-term research center. So it was basically very academic research. And so when I switched to real academia, I often joked that I had much more academic freedom in industry because I didn't have to convince anyone to pay for it like I do now. But I think one thing I learned in industry, and also since being in academia, talking to people in industry, in academia we really serve an important there's an important reason for us from the industrial perspective is that they're really looking at us to come up with ideas that maybe will be important for them in 10 years, 5, 10 years or longer, something that they're not thinking about because they're so focused on the immediate problem. And so I think we both have a role to play, I guess is what I'm saying. They have their problems that they have to solve right away. We have a role to be looking more forward toward the future. But I do have to say that I've been very selfish in my career. I have problems that I'm interested in, and I've always been fortunate that someone else will pay for that. And so I've had the luxury that I get to work on problems that I really love to work on. So.
Also, like in your early career, you had the good opportunity to work with, like 2 Nobel laureates now. Can you like tell us the learnings that you like learned from them?
Yes. So again, a complicated question, but I'm going to stress something that I learned from each of them, but that doesn't mean the other one was not like that. So Bawendi, my PhD supervisor, he's very humble and soft-spoken if you ever meet him, but he really values excellence. So he likes to understand something at a really deep level, and that's something that all of his students really learn from him. So there's none of this, I'm great, big ego, but just let's focus on doing good science. W. Moerner, who was my postdoc supervisor, he taught me a lot about discipline. So he's very disciplined. I remember being surprised when I first got there. He went to every seminar that came on the schedule, and he would go and sit and take notes, and he really he would read papers. He would give us papers that he'd read that had his handwritten notes on. He really studied the field that he was in at a very high level. The other thing I wanted to say about the Nobel Prizes, so both of them got Nobel Prizes for things that happened when I was there. So first with Bawendi, it was something that I was involved in. And for Moerner, it was something that one of my colleagues was working on, and I didn't have anything to do with, just to be clear. But in both cases, looking back, at the time, we had we thought, okay, this is a really nice, important result, but there was no, like, we didn't go out that night and celebrate because, this was a Nobel Prize winning result. So I think only because of all the research developments that were done after that, it turned out that that result, which was important at the time, but became important enough to win a Nobel Prize. So I tell everyone now, like, you don't know, if you have a nice result, you don't know what's going to happen with that result. So it's just good to do good science.
So you mean just to enjoy the process?
Well, that, and of course you should do something good, so you should try to work on important problems. But any good result, I think, the lesson I learned in the case of the two anecdotal situations that I was in, any good result could, in the proper circumstances, turn into a Nobel Prize.
So now we are almost at the end. I would like to ask you, like, if you have 3 advices that you would like to give the young people who are just joining science or like paving their own way into the stream.
Yes. So I think one thing that frustrates me often as a professor, and in some sense, one of my colleagues jokes that what a professor really is a professional evaluator. We're just always evaluating either student exams or student presentations or their theses, or when a university is hiring, you're evaluating candidates. And there's this tendency now, which I don't think is a good thing, that everybody tends to work on the same problem. And then they all write proposals about what they want to do, and they're all basically working on the same problem. And I would like to encourage people to do something different, find something they're interested in, and hopefully it's an important problem that you can find that you're interested in, and study and work on that, because in the long run this will be much better than just following the herd.
Any other 2 advices that you'd like to give?
Yeah, I was talking earlier that I find that a lot of the super talented young people that I work with, they now make decisions for kind of short-term quality of life instead of thinking about what's going to make them happy in the long run. And I think, of course, sometimes when you're young, you have to not suffer, but you have to do some things that maybe are not fun at the time because you're trying to get to a longer term goal. And I would like to encourage young people, especially that want to do science or engineering, maybe to make some of those sacrifices to make sure that when they're in their 40s and 50s, they still have a fulfilling job. And that couldn't be in many areas. I'm not saying it has to be in academia, but not to make decisions always on short-term outputs. I think this is something that when you're young, maybe you don't appreciate as much as you could.
So I think this is the end, and thank you so much for this interview. It really means a lot to us.
It was my pleasure. Thank you for having me here.
Thank you.